Welcome, physics students, to a special variation on one-dimensional motion problems. This is a special category of problems called vertical motion. And I want to make a distinction here, particularly since there's a lot of discussion around rockets and SpaceX and so forth, which is certainly a form of vertical motion, but we want to talk about objects right now that don't have their own means of propulsion, things that are maybe tossed in the air or shot in the air or otherwise launched in the air, but without their own kind of propellant like a rocket might have. So, shooting an arrow in the air or tossing an apple in the air, shooting a basketball, or all kinds of things like that, generally fall in the category of free fall, in that once they're given some initial energy, they are essentially constantly being pulled back towards the Earth in a free fall situation. All right, so if you can identify a problem as a vertical motion problem, there's some information that you can bring to bear right away. The first thought is this, that we are going to define upwards as positive and down as negative, which I think makes a lot of sense. If you want to throw something to the top of a building and you figured out the change in position at the end of the problem, you would want that to be a positive number. It just sort of makes some intuitive sense, that the height of the building would be plus 15 meters or something along those lines. It would be silly for that to be negative. Well, if up is positive and down is negative, then right at the peak, we must transition from positive to negative, and the only way to do that is to have a velocity of 0 for an infinitesimally small moment. So at the peak, we can assume that the velocity Vf is equal to 0. So one consequence of this convention of up being positive and down being negative is that at the peak, the velocity must be 0. Okay, what else can we say here? The three equations of motion are still valid, so the delta P equation and the two variations on Vf are still valid, and so they can be used, but there's this bit of information that at the peak the velocity would be 0. If we release an object, if we're, say, at the top of a stairwell and just drop a bowl of soup, the initial velocity is 0. If we neither throw it up nor down, if we just release it, then we can assume the initial velocity is 0. And then, and this is a kind of a very interesting idea, if we are at or near the Earth's surface, then all objects will suffer from the same acceleration towards the Earth, independent of their mass. They'll all accelerate towards the Earth at with a value of minus 9.8 meters per second squared. So the acceleration is a given. If it's a vertical motion problem, you don't have to figure out the acceleration. It's a given. It's minus 9.80. Galileo proved this with two different spheres of different masses from the Leaning Tower of Pisa in somewhere around 1620. And you can see a really nice example of this at this particular link. It's a YouTube video that will bring you to a terrific demonstration of two objects falling with very different masses in a vacuum. And what that'll do is it will eliminate the confounding issue of air pressure. Most large-scale objects will experience some air pressure, of course, or air resistance, but because they're massive enough, they'll kind of fight through the air reasonably well, and you really won't see much of an impact. But if you have something light and with a lot of surface area, like a feather or a single sheet of paper or something like that, you obviously will see the impact of air resistance quite a bit. And so it seems like this particular statement that all objects will accelerate at the same rate is not quite the same, not quite true. It is true, but in those cases there's a counteracting force of air resistance that we would normally neglect. What I want to just add here is that if you do go, the link here is posted on the Google Classroom, and you can access that to see a couple of different steel balls fall in a vacuum at the same rate as a feather, along with a clip of a similar experiment done on the moon. Okay, I'll take just one more moment to kind of look at the velocity graph of something like this. If we were to graph the velocity versus time for, say, a tennis ball thrown in the air, then we would pick up the problem. We've got velocity versus time, and when time is 0, that's when it comes out of your hand with some initial velocity with the object thrown upward. And as it ascends, it will eventually get to its peak, and at that exact moment the velocity will be 0. And then finally, as it comes back down, you see the velocities are negative, so it will start to pick up speed, quote unquote. It'll go faster and faster. It's further and further away from 0, but in the negative direction, so all those velocities are less than 0. One last comment: the slope of this line, if indeed we're at or near the surface of the Earth, would be minus 9.80 meters per second squared. Okay, so that's a little bit of background for you of a very special case of one-dimensional motion problem known as vertical motion problems.